6.6, we're going to look at using proportionality theorems. Some of these occur within triangles. Others occur when we're talking about parallel lines and transversals. So again, we'll just kind of take a look here and see what you think. So the triangle proportionality theorem simply says if a line is parallel to one side of a triangle, intersects the two other sides, then it divides the two sides proportionally. So in other words, TU is kind of in the middle of this. TU here is in the middle of this triangle, and it's parallel to the third side. And so what that means, it cuts the two sides proportionally. In other words, TR over TQ is going to be the same as UR over US. Okay, so it cuts it proportionally. There's actually a few other proportions you could write here. You could have written a few different things, but the big thing is staying consistent. Okay, and I'll explain more of that as we look at some examples here. The converse of the theorem we just said says very simply, if the sides are cut proportionally, then that means that TU, all right, and QS have to be parallel segments. It's just, again, the converse of the theorem. So in example 1 says find the length of QU. All right, call it X. We don't know it, let's call it X. You could set this thing up a variety of different ways. The way I see it, 10 over X, 12 over 6. Okay, someone else could come across and say, no, I see it as X over 6. And if you do X over 6, then you better do 10 over 12. Okay, someone else could come in and say, no, I see it as 12 over 10 is equal to 6 over X. It doesn't matter which one of these proportions you use. When you cross multiply, you're going to get the same thing. 12x equals 60. Divide both sides by 12. X equals 5. Okay? That's the length of QU here. So that's why I say just be consistent. It doesn't matter how you set it up. Just make sure you are consistent throughout the problem. It says find the length of KL. Again, I don't know KL. Let's call it X. So the way I see it, let's set this one up differently. We're going to say X over 44 equals 18 over 24. If you want, you can actually reduce down the right-hand side here first to get you nicer numbers to work with. In other words, you can do X over 44 equals 6 goes into 18 3 times and 6 goes into 24 4 times. Completely up to you. You don't have to do that, but you can. So now when I cross multiply, I get 4x equals 44 times 3 is 132. Divide both sides by 4. Tells you that x equals 33. Okay, x equals 33. Example 2, determine whether or not the two lines are parallel. Well, if they're parallel, again, it cuts it proportionally. In other words, in order for them to be parallel, 18 over 38 has to equal 36 over 80. A couple different ways you can do this. You can just very simply reduce down both sides, or you can cross multiply and see if you get the same number. It's not going to matter either way. I prefer to reduce. So when I reduce, I know 2 goes into this guy 9 times, 2 goes into 38, 19. So that's 9 over 19. I know 4 goes into 36 9 times, 4 goes into 80 20 times. Clearly those are not the same, so the answer here would be no, they're not parallel. Okay, because they're not proportional. If we know that, okay, example, part B here says, if we know that AB is 31, and BC is 19, and CD is 27, and DE is 23, determine whether or not the two lines are parallel. No different than what we just did. All right, so we have 19 over 27 equals 31 over 23. All right, and so when I look at that, I'm pretty sure I can't reduce them down on either side. And if you're not sure, you can always just cross multiply. When you cross multiply here, 19 times 23 is 437, and 27 times 31 is 837. They are not equal, therefore they are not parallel. Okay, so that's all we're looking at here when using the converse of the theorem. Theorem 6.6, again, you won't have to memorize this, but you'll have to be able to use it. If you have 3 parallel lines cut by 2 transversals, then they divide the transversals proportionally. Okay, in other words, when you look at these transversals, you have 1, 2, 3, 4 pieces that they kind of get cut up into, and those pieces are divided proportionally. In other words, UW over WY is the same as VX over XZ. And again, it all comes down to being consistent. You could set it up a few different ways, but you got to be consistent. All right, so when I look at this example here, the way I would see it is I would do 24 over 32. And since I did 24 first, I better do 27 first down here. So I do 27 over, call the length of AB X. And now we're right back to square one. We're going to cross multiply here, so I get 24x equals, I have 32 times 27. So when I plug that in, I get 864. And now I know I got to divide both sides by 24 to get x by itself. So I do divided by 24. X equals 36, and 36 was represented AB, so I don't have to do anything else there. It's not like I have to plug it back in or anything. Example 4 says a farmer's land is divided by a newly constructed interstate. The distances shown are in meters. Find the distance CA between the north border and south border of the farmer's land. Okay, so in order to find the full length of CA, I first have to find CB, call it X. Okay, you have 3 parallel lines cut by 2 transversals, so they are cut proportionally. X over 2,000 equals 3,000 over 2,500. Cross multiply, 2,500x equals 6, and then we have 6 zeros. 1, 2, 3, 4, 5, 6. Divide both sides by the coefficient of x here, 2,500. And you find the length of CB here to be, let's see here, 6 million divided by 2,500 is 2,400. So this length is 2,400. The question is find CA. Okay, so if I want the full length of CA, I have 2,400. I have 2,000. 2,400 and 2,000 makes 4,400. And again, these are in meters. Okay, so that would answer our question. The full length is 4,400. Okay, and then I believe this is the last theorem we're looking at today, and that is Theorem 6.7, which says if a ray bisects an angle of a triangle, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. In other words, AD over BD is the same as AC over BC. Again, be consistent. A few different ways you can set this thing up. So example 5, we're using this theorem now. So the way I see it, personally, I would do x over 5 equals, and then over here I better do the 18 first, 18 over 15. Just make sure when you're doing it, everything's kind of lining up. So you cross multiply here, you get 15x equals 50 plus 40 is 90. Divide both sides by 15. So the value of x here is 6. Part B, a little bit tricky here now because the length of GF is not given to you, but you can form an expression that represents that length. In other words, if the whole length here is 14, this much is x, then you know that this piece, GF, has to be 14 minus x. Okay? And so now you're right back to square one. Okay? Set up proportions and solve. I would personally do 8 over x equals 12 over 14 minus x. Cross multiply, make sure you distribute the 8. 8 times 14 is, let's see here, 80 and 32. So 112 minus 8x. Add your 8x to both sides. So you get 20x equals 112. Divide both sides by 20. And you find that x equals, it's going to be 112 divided by 20, 5.6. All right, so x is 5.6, and again, that's just kind of showing you. Again, it's a little bit different because you have to create this expression there, so it makes it a little bit tougher. All right, and then finally, example 6 here. Find the length of AB. We don't know it. Call it x. So again, now it's right back to square one. Okay, we'll do 3 over 1 equals. Now you do x over 2. Cross multiply, x equals 6. Done. That simple. Okay, so some of these are more difficult than others, but for the most part, these theorems work out pretty well. Just cross multiply and solve for your variable. So that summarizes section 6. As always, any questions or concerns, we'll work through things and hopefully resolve issues in class.